start recording.
Okay.
Okay, let's get started. Good morning, everyone. Welcome back to SNAPP seminar. Today we have Andreea Minca from Cornell. She's an associate professor in the School of Operations, Research and Information Engineering at Cornell. She received her PhD in applied math from University of Paris, and she studies financial networks and uses mathematical modeling to derive optimal policies that promote system stability. She has made fundamental contributions to understanding of financial instability, quantifying and managing systemic risk, and control of interbank contagion. In recognition of these contributions, she received several awards, including 2016 SIAM Activity Group on Financial Mathematics and Engineering Early Career Prize, NSF Career Award, AXA Research Award on Mitigating Economic Effects of COVID-19, and she was also 2014 GARP Fellow. Today, she's going to talk about contagion risk modeling. And without any further delay, Andreea, the floor is yours.
Okay, thanks a lot. That's a very nice introduction. It's really a pleasure to be here. So I'm going to be talking about contagion risk. As you said, most of our motivations were coming from financial networks, but I would say that especially in the current context, this is a topic of interest in general. So this is work that we've been doing with Hamed Amini, who's hopefully here, who's going to answer all the questions in the chat. And with he's at Georgia State University, and with Sulem, who's at INRIA. And the paper is available online, so it's same title, Dynamic Contagion Risk Model with Recovery Features. Yeah, and I'll base my talk on that. Okay. So as I said, we've been working on systemic risk for something like more than a decade now. And of course, I should define systemic risk. That's a risk that emerges in an interconnected system, and it comes from the interaction of components. And most of our work was on the network side of this. So in a network, the way we define systemic risk is really the way the network amplifies an initial shock. So initial shock is going to hit certain nodes, and then other nodes are going to be exposed to those initial shocks, and then it is going to be propagated in the network by, and then of course it depends on the model of propagation. We have looked at random graph approaches as a tool for systemic risk modeling. And of course, when you talk about random graph, one should really be somewhat careful, because a random graph, it means that you do not know the exact network. So you might ask yourself under which circumstances you would use a random graph approach. Now, in finance, it does make sense, because the exact network of who is connected to whom is not entirely known. So in general, when you look at financial networks or even economic networks, you take a bird's eye view, and you sometimes place yourself from the position of a regulator, but a regulator doesn't have full information on everything that is happening at the level of the linkages. So in particular, they would know some aggregate information that is at the node level. For example, what is the total, how interconnected, let's say, a bank is, what is the total size of liabilities, what is the total size of assets. So if you want to think about assets and liabilities in mathematical terms, you depending on how you choose the direction of connections, those would be weighted in degree, weighted out degree. So then in a random graph approach, you basically know the weighted in degree, but not how the weights are distributed on the edges. So that's the bottom line. So there is this missing information on linkages. And then, of course, as I was saying, and as I was hinting, you want to categorize nodes according to some of the characteristics. And what are the characteristics that you're interested in? You think about regulators and what do they know about banks, about firms, about whatever you are modeling. So do they know this weighted in degree? Do they know the degree? Do they know other characteristics? And then you would say that within each category, nodes are exchangeable. So that is what we do in the model. Now, you know, when you think about random graphs and you want to have a real world application, you have to think about what type of results we are going to be obtaining. And the analysis in general is asymptotic in nature. So you want to have networks that are sufficiently large. And therefore, when you think, for example, about banking networks, you might want to think about the level of an economic area. So think about an entire economic area, and you want to have something of the order of several thousand banks for the asymptotic analysis to be relevant. The other thing is that in general, the random graph that we are working with and which are tractable, and they have what you call locally tree-like properties when the size of the network goes to infinity. So locally they behave like a tree. Whereas when you think about real world networks, of course, the first thing that comes into mind is the fact that they have small cycles. So examples of these random graphs that one works with, of course, the endoshreni random graph configuration model is the one that we work with in homogeneous random graphs. We have also used that in the past as models for financial networks, preferential attachment models. So now, then you balance, advantages and disadvantages of certain of these models. The configuration model in particular is very tractable, so you can get a lot of nice results. And then recently there has been work in which we can introduce clustering, and so it's a model that is quite I would say quite robust, and it's tractable, and it has the advantage that you can put a lot of extensions into it, and still you get nice results and remains tractable. So in general, we have used this model, and the talk I'm going to give today is going to be using this as a basis for our model. Okay. So what we are, of course, so this is the underlying model for the network. We were thinking about indeed about economic networks of firm, but as I said, it's not necessary. You can move away from these details. Now, for the model of contagion, we are looking at threshold contagion models. So threshold contagion models, I'm sure many here know. The basic idea is that you have nodes, and nodes are endowed with thresholds. And then when the neighbors of those nodes fail, then the linkages between the nodes, you can think about them that they have failed. And each node has this threshold, and the threshold itself says how many failed links the one node can withstand until it is going to fail itself. Okay, so you have the neighbors, and among the neighbors, a few of them are going to fail. Let's say 5 of them fail, and if the node's threshold is 4, then the node is going to fail as well. And when the node fails, then it is going to impose also, it is also going to be linked to other nodes, and those nodes may fail in turn because their threshold might be reached, and thus propagates a cascade in this independent threshold model. And independent means that basically the thresholds are assigned independently. But of course, this is not, this has been extended, and you can have other types of models. What we have done in our work and in this paper is to look beyond the classical model of contagion, which was essentially static, and introduce some notion of time, and also look into the idea that these thresholds are not necessarily fixed. So you are indeed endowed with a threshold that says how many failed linkages each node can withstand. But of course, if you introduce a notion of time, then these thresholds can in fact increase. So obviously this makes sense in financial networks, because contagion takes time. So it's not like a node fails and immediately the neighbors are going to be affected. So this, there's a process by which the failure from one node is transmitted to the neighbor. So this takes time. In the meanwhile, there can be recovery. So recovery means that the threshold might increase. You can think about insurance and reinsurance networks. In insurance reinsurance networks, you have the primary insurers that insure certain risks, and then they go to bigger firms in global firms, and those firms are acting as reinsurers. But then of course the reinsurers have other reinsurers in turn, and so this becomes a global network. And there it makes a lot of sense to consider that thresholds are increasing, because as contagion happens, as there is risk that is materialized in the system, premiums are getting paid. So you can think about the threshold, of course, as capital, liquidity buffer, and as premiums get paid, then this liquidity or capital buffer increases, and then firms are able to increase their threshold and withstand more losses and more failed linkages. Now, you can think about our model as also a set of what is called Cram er-Lundberg process. And if you haven't heard about it, don't worry, I'm going to define it a bit later. So those are processes that are used a lot in insurance. In fact, they have a part that has a linear growth. So maybe I can show how a typical process looks like. So kind of like this. Okay. So if you have over time, you start with a certain capital here, then it increases, and then at some point, here the usual one-dimensional thing is that you so after an exponential time, let's say, then you have a jump down, and so you go here, then you have some other period of growth, and then you have another jump down here, so that then here you have some exponential time, and if this jump is too big, so it takes you below zero, then this is defined as a default. So this would be a basic model that is used in insurance, and the basic thing is that here you have some distribution for the losses, and the inter-arrival times here, they are exponential. But of course, you have other distributions and so on. And now think about it, where this would be a one-dimensional process. So this would be for one insurer. Now think about it. What happens if you put this kind of processes living on the nodes of the graph? Well, this inter-arrival time, so this is the moments where losses happen, they are no longer exogenous, they're no longer that's the important thing, they're no longer exogenous, so they happen. So here this arrival of a loss, they come maybe from somewhere else in the network, right? So from another node, so this is another node who has failed, and then this is a linkage that has failed, and then the failure of this link is going to affect the, the risk process, or the kind of the capital or the liquidity of the, of another node. So think about it like, you have this interconnected guys, and then it will look like this, something like this. Okay, and each one of them is going to have some type of process of this kind, but the idea is that, of course, the arrival times of the losses for each one of them are going to be linked with what happens to their neighbors. Yeah. So now of course, where we are going with this, towards, trying to understand. We have this model. There's a independent. There's a contagion model with some time dimensioning with growth, and then what are we going to do about this? Of course, agents know about this potential contagion risk. And you can think about them as choosing their connectivity. So in a configuration model, there's not too much to choose, because the random graph is first we assign the connectivity, and then the graph is created by uniform matching. But then at least they can choose their connectivity, how many connections they should have. So you can think about that as a connectivity game, and this is something that we are also looking at in the paper. Okay, so let me tell you about the model. So the details of the model. So you have n nodes. So we can think about them as agents in the part where they are going to optimize their connectivity. And they are endowed with a sequence of initial thresholds. And for simplicity, we assume that the in degree equals out degree for each node. I mean, it doesn't pose a problem for the asymptotic result to relax this assumption. For the connectivity game, one should be careful. It might change some of the part of the game and part of the interpretation of the results, but in general, changing the in degree and out degree doesn't pose any problem. So as for simplicity, we assume they're the same. We assume that, so as I said, the basis for the network model is a configuration model with this given degree sequence. Of course, we need some regularity conditions on the degree sequence and thresholds on the degree distribution. So here is a hidden notation, the degree distribution, I'm calling this, so it's going to be in the network of size n. This is the fraction of nodes that have degree lambda and threshold theta. We do assume that in this paper that this distribution has a finite second moment, but we suspect that this is not necessary. So, and indeed there have been recent results, not on contagion model per se, but on giant component problems, and they do not need this kind of assumptions on finite second moment. So we suspect that this is not necessary. Now, in our models, and in general for network models of contagion, we assume that after the network is formed, you have a shock that occurs. So it starts from, and then contagion is going to start from a set of nodes, this D0, that is selected exogenously, and we call them initially failed nodes. So exogenous set of, here I should write initially failed nodes. And now this initial set of failed nodes is going to trigger a failure cascade, because the failed nodes affect the nodes connected to them. And in which way? Yeah, please.
Are those deterministic, those D0?
D0 is not deterministic now. So you can, no, they're not deterministic. You can choose them,
according to some
numerical results. We can choose them. We're going to choose them uniformly, but you can have a certain distribution. You can choose them across nodes who have who have certain degree. You can say I'm endowing certain nodes with threshold 0, which means that they are they are failed. But then, okay, as I was saying, in this model you have asymptotic results. So you can say, for example, you can say that among among the nodes with degree lambda, a certain fraction of them initially defaults, but it wouldn't matter. You can't choose who of these guys is in default, so it's not going to be deterministic in this sense. Okay, but you can do a bit more than uniform, than choosing them uniform.
It can depend on the initial degree.
Yes.
Okay. Thanks.
So in general, you can put like characteristics. You can make it depend on initial distributions and things like that. Yeah.
Thank you.
Okay, thank you. And please don't hesitate if there's other questions. Please just jump in. I can't really monitor the chat, so I hope that yeah. Please go ahead if there's any questions. Yeah. So as I was saying, you have this initial set of failed nodes, and then they affect the nodes connected to them. And how do they do that? Well, whenever the threshold, so a neighbor's threshold is smaller than the number of failed incoming links, then it fails due to contagion. So just maybe I can do a small drawing here if I have like a bit of space. So say that this guy here is failing, and now this guy is his neighbor, so this guy now it's failed. Okay, and then this here, it has a connection to the failed node. Let's say that the direction of the links is like this. Okay, and now let's say for the sake of this example, the threshold of this guy here, theta I, so this is called I, theta I is equal to 1. Well, because he was exposed to one failed node and his threshold is equal to 1, then this one is also going to fail. Okay, and let's say this node over here, the initial one, is connected also to another node, call it J, and let's say that theta J is equal to 2. Well, in the initial step, J is not going to fail because his threshold is 2 and he has only one incoming failed link. But now, okay, imagine now that secondary he has, so this I is now in default, and now imagine that incredible lack of luck, he was connected also to I. So when I fails, then this other link, so I should write, this is a failed link, this is now a failed link. And now also J is going to fail because initially he had, well, actually this one also was a failed link. He had one failed link from the initial node, and now he has also a failed link from I, and his threshold was 2, so then J is going to fail as well, and then it's going to propagate to the neighbors of J and so on. So I hope it's clear. This model is a very famous model. Oh, I won't enter so much into the details of it. So what we do is introduce a notion of time. So we now say, okay, we have these thresholds, nodes are endowed with thresholds, and we're going to say, well, we have a global growth rate per unit time, which is alpha times n. So this is the, just go back to the financial example and think about it as the rate of growth per unit time of the entire capital in the network. And it makes sense that it scales with n, with the size of the the network. And note here that it is per unit time. So we do need to introduce a notion of calendar time, because so if you go back to this very simple thing that I wrote, well, what I was saying is that, okay, take this guy fails, then it's going to impact this node I, is going to impact this node J. Well, these are not, there's no time notion here, it's just an interaction, and you can describe it in a certain way. You can say, okay, let me take this one first, this interaction first. Okay, you can think about it in terms of interaction time. So you need to find a way to put a notion of calendar time if you want to introduce growth. So one assumption that we make is that so this global growth is going to be distributed proportionally to the node's number of links. So if you have a node that has connectivity lambda, then a node with connectivity lambda is going to grow with the rate per unit time, alpha times lambda times the average connectivity in the system. So this is the formula. Yeah, probably not very interesting. Yeah, so here's the dynamic model of contagion. At time zero, you have this set, this row of nodes that fail exogenously, and now how the simplest idea how to introduce this calendar time, you say, okay, between two successive interactions, I'm going to take exponential of parameter n. So then the average time between interactions 1 over n. So what does it mean? So take my this node that is, call it whatever you want, 0, and then this one had, if you recall, had 2 linkages to node I, and then here it was to node J. And now, well, we said that this guy is going to fail. So initially nothing happens, but each of the links here that fails is going to have an exponential. So it's going to have an exponential clock. So here you're going to get an exponential, and here you're going to get another exponential, and then whichever clock is going to go first, then you're going to reveal this link. And initially I said, okay, take the link between 0 and I. Okay, you can imagine that that's because this exponential clock was faster than this other one, and we make it such that at the level of the network, the exponential time is 1 over n. And yeah, I probably shouldn't enter all these details again, but basically in the model, if all the links that exit from failed nodes, so in particular this was a failed node, and imagine there's other failed nodes, they all are assigned exponential clocks. And then we are assuming initially that at the level of the network, we have an exponential clock, and the average time is 1 over n. Now, I'm going to state this in the open questions. You might want to have an exponential clock. The average time between interaction might depend on the state of the system, and so on. But this is really the simplest case. So now, between two interactions. Yeah.
The exponential clock is for what purpose on the failed links? Is that to rebuild them, or what happens at the times of the clock?
Well, what is the purpose of it is so from a modeling perspective, it's more like you wouldn't know immediately. So say that this is a bank and this is another bank. Those are 2 other banks. You would model the fact that, okay, this one has failed, and then you try to find out who was connected to them. So it's not entirely obvious who had connection. Like even there was this hedge fund that's
the time it's revealed to the neighbor.
Yeah, that is the time that is revealed.
I see.
Yeah, so that's the time that it is revealed. So, and then it's very unlikely that everything's going to be revealed at the same time. Now, that said, also this has the advantage of making the model, quite tractable, because you, this is going to become a Markovian system. So it's going to be really nice, and then it's going to have you're going to be able to scale things and get the asymptotic results. But yeah, in general, if I'm to to explain this, this is really the time. From a modeling perspective, you want to not everything gets revealed at the same time.
I see. Thanks.
And also, yeah, it's if it's also by the time that we have learned that this guy was exposed to 0, maybe his threshold was no longer 1. You remember in my initial, well, on the previous page, I had said, threshold here was equal to 1. But then, okay, maybe by the time we reveal this link, its threshold is no longer 1. So the threshold has also grown. And you can think about it in various ways. Okay, it may not be revealed, but and obviously the longer this takes, the better for the nodes, and the more they can the less likely it is that they are going to fail. Yeah, so now threshold will grow between 2 interactions, and now any surviving node with lambda outgoing links and initial threshold theta is going to have now a threshold theta plus alpha. So this is, as I was saying, this is the rate at which the threshold of nodes with connectivity lambda will grow. So you have this one, and then up to the case interaction, this is TKN. So this is the sum of all this of all the deltas up to the case interaction. So they might get a lot of growth in the threshold. So links that belong to the failed links are revealed one by one. So according to the exponential clock, initially all these links are unrevealed, and then if the number of failed links of the counterparty exceeds its current threshold, so if what was it, was J, so it was J also had some connection like this. So if the number of failed links here is going to reveal the threshold, after the growth, then the node will fail and its links will also become unrevealed. And then you have the cascade that progresses until there are no more unrevealed failed links. And then you can group the nodes according to, you can group the surviving nodes according to their initial threshold, the outgoing links, and how many failed incoming links you have. They have, and this is going to be a Markov chain. So that's really nice. And if you don't have growth, this is quite easy to study. And I'm just going to give the theorem for the case without growth, just to show you how this looks. So you want to find this quantity here, which is the final fraction. So this is final fraction of failed nodes. Failed nodes. Okay. And how do you do that? Well, we prove this by by looking at, by studying this Markov chain and using the whole machinery Wormald differential equation method. So you take this this kind of this Markov chain, you scale it by n, so it's a fluid limit, and then you use the differential equation method, and then you have the fluid limit. But there is a very simple interpretation. So you can look at at the equilibrium of this cascade. So, and then you say, okay, I'm going to take a link. Let me see. I'm going to take a link like this. I'm going to enter a node, and then so no, actually I think it's the other way around. So the direction should be like okay, so the direction should be like this. And so this is a link. Can't I erase? Yeah, it's better. So. So I'm going to take a failed link. So this is going to be a failed link. Okay. This is going to be like this. So this is a uniformly chosen link, and then I want to say that the cascade is finished when the probability that this link is failed. You can think about it as a fixed point. So when is this link failed? Well, if it comes from a failed node, so it's gonna, this link chosen uniform is going to be a failed link if it comes from a failed node. So this guy needs to be failed. Well, when is this guy failed? Well, if this guy is failed if its threshold has been met, but by its own number of incoming failed links. So this link is failed, and then this guy maybe had a threshold theta, and among its linkages, we had a bunch of we had at least theta which were failed. Okay, and then so what does it mean? We're going to look at a fixed point of this function. So we're going to be looking at j of pi is going to be equal to pi. So let's say that pi is the equilibrium probability. So equilibrium probability that the randomly chosen edge is going to be failed. And you want this to equate to the probability probability that that this node over here is failed, and the probability that this node over here is failed is exactly this one. So this is the probability that a binomial distribution. So this node here has a degree lambda, binomial distribution. So you choose among its edges, among its incoming links, with probability pi, the ones that have failed. So it would be this one, and then you get you get among the lambda incoming edges, you choose them with probability pi, and this is the probability that this node here is failed. So, and then of course you look at the distribution, and this is what is called size bias distribution, and of course this is the probability that this node over here, which is linked to which is the end node of my randomly chosen edge, has degree lambda and threshold theta. And this is the size bias distribution. It's this idea that your friends are, a friend of yours is most likely to be to have more friends than you do, and this is because it's not a randomly chosen node, but it's a node that is the end node or the beginning node of a randomly chosen edge. So you find this pi, and this pi is going to be, as I was saying, it's the probability that a randomly chosen edge in the network is failed. And in the sequel, I'm going to call this global failure probability. And yeah, so you find, you say that the cascade is going to, so intuitively the cascade it has found its equilibrium when you can say that this pi is equal to this j of pi, and then very easily you can find the final fraction of failed nodes, which is so this is the probability that a node with degree lambda and threshold theta is in default for the, and you plug in this global failure probability. So global failure probability. This is the pi star, and this pi star is the solution for this j of pi is equal to pi, right? So this is, okay, this is the solution of this. And so this is without growth, and starting from that you can
ask a quick question.
Yeah, starting from this you can find the ones that are surviving. Yeah, please, question.
Was there an implicit assumption that you don't need to keep track of the type of your links, that pi is just the probability that a neighbor fails irrespective of their type?
No, so this is just what I said in the last one, is just an intuition, just to parse, you know, the formulas. In the proof, of course, it is the model that I explained, and it is studied by the all of these emerges from studying the scaling limit for this Markov chain. You of course, when I wrote here binomial distribution and so on, it will look like things are independent. Of course, they aren't independent, but this is what comes up in the limit when the graph is large. So we do not need to assume. I mean, this is not how you derive the formula by looking at the drawing. This is just an interpretation. Okay.
Okay.
Yeah. So going to the case with recovery features, in fact, it's a little bit more complicated there because you have a first passage problem. So in the case without growth, it is you only are going to keep track of the number of failed linkages of a node. But here with growth, you have that the failure node, the failure of a node is a first passage problem. So how does it look? Well, you have your, you know, kind of like, you have the cumulative failed link process. Then here you know, at some point after an exponential clock. So first I have no failed links. I'm a node. I have no failed links. Then after exponential clock, I learned of a failed link. So failed link is revealed. Then this grows like this, and then it grows. You know, stays. You know, stays here, then it's going to grow and so on. And so this is the cumulative, and then these are not constant. So these are, again, they are not exogenous. So this here is not exogenous, or not exogenous. So it is these exponential clocks that come from the network, and this is how this cumulative failed link process for one node looks like. So these are the exponential clocks. So exponential clocks that govern the failed links of the net, failed incoming links, right? Links. Okay, and now you want to check that this hasn't passed at any point in time this cumulative, this threshold process with linear growth. So obviously this is just linear, and then so for example, it's in the previous case where so when you look at the case without growth, well, this is doesn't look like this. Actually, I should have not quite like this. It starts from a certain level. So let's assume I'm not intersecting it anymore. Okay, so let's say like this. Well, in the previous case without growth, it's not a line, so it's just a level of threshold. So that would be theta, and this is the growth. This is the threshold. Well, it's a bit harder because you have to check at all possible times if this. I'm not pleased with the drawing. Let's see. Okay, so let's say my initial threshold is kind of here. So that would be a theta. And you see, if the theta was kept constant, I wouldn't need to keep track of anything. It would be very easy to see just by looking at the end level of the, you know, of this cumulative failed link process. I just need to look at where it arrived at the end. But because you have this linear growth, you need to track. Okay, here they have crossed, and then this particular bank is defaulting in this case. Now, surprisingly, you have very similar formulas, and then it's a little bit more involved, but you can still compute this fixed point that gives you the failure probability of a node in the system. And if you look at the theorem, it looks very, very similar to what I was showing for the case without growth. And what will change, of course, is that this probability of default is different. So it comes from this calculation of the first passage problem, and then but other than that, other than this calculation, things are quite similar, and we still have the problem remains tractable. Now, yeah, I'm looking a little bit at the time. We do have results on existence and stability of a fixed point. Now, as I was saying, for the proof steps, we aggregate nodes according to their connectivity, their threshold, number of failed counterparties. As I was saying, we use standard machinery. The application, however, is quite tricky because you have these complications like the state space increasing with time, and this comes from the fact that the threshold increases over time. But still, we have these results, and you can compute the stopping time of the cascade and relate this to this global. So this is again this probability that a randomly chosen link fails, and the stopping time of the cascade is related to this phi star by scaling with lambda star with the average connectivity in the system. And now, the rest is quite easy because it's about defining the game in this model. And the basis of this game is, okay, this phi star, which is the failure risk. And this can be used to define the node's performance criteria, define their connectivity optimization problem. So now, as I was saying, there is this trade-off, of course. As nodes are going to add more connectivity, they are going to increase their risk of contagion. And it's a very, what kind of reward are we going to use? Well, a very simple one. If they choose a degree lambda, then their reward is going to be lambda. So this is my degree, and then here, this is my survival probability. So I'm going to say that I have the higher my degree, the higher my reward. Of course, if we look at what everybody else does in the system, this is where everybody else's decisions are going to be aggregated, because the individual's survival probability depends on what everybody else is doing and choosing. And in particular, the choice that they have is on lambda. So the timeline is as follows. So the nodes receive their thresholds. The distribution of the thresholds is common knowledge. Now, based on their thresholds, they're going to choose their connectivity. Then the network is formed according to the configuration model, is subject to an exogenous initial shock. Now, contagion ensues from this set of exogenous initial failures. And then we choose those with fixed probability among all nodes for simplicity, but we can make other, as I was saying, we can make other choices, it can depend on the distribution and so. Yeah, and so the kind of equilibrium that we're going to be looking is a rational expectations equilibrium. So nodes are going to choose their connectivity according to an expected, so they expect a failure probability pi of a link, and then the equilibrium condition is going to be that the expected failure probability of a link coincides with the actual failure probability under the optimal connectivity. So just to show you how it looks, so you recall the asymptotic reward. So then a node with threshold theta is going to maximize this reward, and then pi, so this is given pi star. So if they were to be given the global failure probability, so the failure probability in equilibrium of the thing, this is what they would be choosing. And then you want to make sure that that this pi star that they were hypothesizing is actually matching the the failure probability that we derive and we have looked into for the configuration model, which is this thing over here. So then you look, okay, you look at all of this, and then you get that this is the smallest fixed point of this map. So this is quite straightforward, this part. And now we also have some results on the convergence. So for the network of size n, you can also define the equilibrium in the network of size n. So everything, these are the same quantities, but not the asymptotic ones. So these are the nodes that fail in the network of size n. There's a fraction of nodes that fail in the network of size n. And then, under certain conditions, then what's going on in the network of size n is going to converge towards the asymptotic quantities, asymptotic equilibrium. Okay, so let me show you a little bit of the numerics. Okay. Maybe not. Okay, sorry about that. Okay, so maybe I'm gonna stop sharing here. I'm gonna take some questions while I recompile this thing. I don't know why. Okay, so let's take some questions while I recompile my slides.
I have a question.
Okay, please go ahead.
So in the simpler setting, when there is no growth, I mean, I kind of see how the whole mean field machinery works, the Warmer method works to give the result that you stated. But in the case of when you have growth, I don't see how it works. Can you tell me more about, because it's much more challenging, right?
Yeah, so the whole thing about when you have growth is that you have to solve this first passage problem. So you have to find this you have to find this times at which there could have been a crossing of the cumulative loss process, if you want. So that one that looked like a Poisson process, but in fact it wasn't exogenous, the arrival times. So you need to figure out, okay, it's a bit of a combinatorics. You do a bit of combinatorics there, and then you say, okay, at the end I've had L failed links, but now I'm going to try to figure out when could have been possible crossing times, and then try to figure out how many failed links could you possibly have between each of these potential crossing times. So yeah, all the details of this are in the paper, and yeah, I probably wouldn't be able to go over them.
Thanks.
Yeah, so let me let me go to numerics where I was. Okay, hi. It's not that it wasn't compiled. It was. Let me try another program. It's because let's see.
You can. We have the slides on SNAPP seminar. You can just use those if you wish.
Sorry?
We have the slides on the website, on the seminar website that you shared with us.
Yeah, it's fine. Let's see if my, okay, let's see now. Share screen. This is my notability. Actually, notability is better than Adobe. Yeah, so now you have, so do you see the slides now with the notability? Yeah, it's good. So you have, so you have, we are looking at regular networks. They have the same initial threshold. And then we are trying to think, okay, you analyze the equilibrium numerically. And here in this part, so you're looking at plotting the chosen the connectivity in equilibrium against initial threshold. And you see that this one is, as you'd expect, it is monotonous. So equilibrium connectivity is non-decreasing in both in theta, the initial threshold, but also as you increase the, so this is the growth 0, and then here you on like this you increase. So here you increase lambda. So you increase alpha, you increase the growth rate. Whereas on the other side, where you're looking at the failure probability, then you have this non-monotonous relation. So then this points to a model has a problem where individual agents choose a higher connectivity because it leads to a higher increase in utility. But then this means that the overall failure risk increases in the system. And then we also look at what happens if you have the initial thresholds that are randomly distributed over a given range, and then you have more heterogeneous systems. And we capture this by the variance of the initial thresholds. So here, you have again global growth rate, standard deviation for this initial threshold, and then in general, so this one is for the chosen connectivity, and this one is for the final fraction of failed nodes. And again, average connectivity general increases with the global growth rate, so with this alpha, and with the standard deviation for the initial thresholds, whereas the failure probability is more irregular and complex function. So it's really not you can't say either way. You have both cases. Now, let me go over a bunch of extensions and open questions that we detail, of course, in the paper. So, as I was hinting initially, one of the interesting things is to look at the epidemic, of course, in the context of maybe medical emergencies that we have seen over the past year or more now. And here the basic trade-off that is underlying the agent's connectivity decision can be reinterpreted. So more connectivity brings the benefits of social interaction, and at the same time they could increase the overall infection risk. So how much social activity do you want to have with how many people you want to connect? So this would be, again, a way to reinterpret this basic trade-off that we have. Other open questions would be, again, as I was saying, what we did there is that calendar time between interactions, that was, if you recall, it was an exponential of parameter n, but you could imagine that it makes, you could extend this to having something that depends on the state of the system. So, you could make the, this contagion happen, or the revealing the links can happen faster or slower depending on the state of the system. And finally, these networked Cram er-Lundberg risk processes that I was talking about initially, well, if I am to write a formula for them, it looks like this. So this would be the capital. It starts from a certain level. Then you have this growth with the parameter alpha I, and then you could have losses that come from the system, from the neighboring nodes, and then you could look at the ruin time of an agent, and this is the basis of how they compute capital requirements for insurers. But of course, in those models, everything is exogenous. So these things they come from the processes are not interconnected. And here what we propose is to look into a networked risk process. And what we have done also can be interpreted from this perspective. We have looked into the case where Lij, so this Lij is going to be a constant, and so and you have L if there is a link between I and J. So that would be a deterministic loss function. What is not deterministic is the inter-arrival times, and those would depend on whenever your neighbors are failing. But the general case would require even more interdependence, because you'd have interdependence between the inter-arrival times of losses. And if I let this L also be generalize this L, then I would also have that the loss distribution is interdependent with the inter-arrival times. Okay, so yeah, so just to conclude, we have introduced this in the usual threshold model, a notion of time, and a notion of growth, more importantly, that is, of course, related to the notion of time. And some takeaways, some economic intuition, that in fact, if you have higher thresholds, they may in fact surprisingly imply a higher default probability in equilibrium, as they lead to larger connectivity in equilibrium. And this moral hazard problem that we have seen. When you have systems with higher growth or recovery rates, you can have equilibrium with higher failure probability and also higher final fraction of failed agents. And yeah, this was well known, the fact that bailouts lead to more moral hazard problems. This was well known in financial networks and financial systems in general. But now, even if you have systems where the threshold is growing over time, as opposed to equity or liquidity infusions, it does happen that strategic agents are going to adapt and potentially take more risks in equilibrium, as captured by this increased connectivity. How to interpret this? It's they anticipate higher growth, and then they take higher exposure to systemic risk, and therefore the growth effect is going to be, is going to be counteracted by the higher exposure. So, what to do? You might want to think what to, how to think about this. Maybe the interconnected agents, the most interconnected agents, you could have impose on them to have higher initial thresholds. Again, I remind you that in financial networks, we can think about that as capital or liquidity. So you might want to have higher thresholds in proportion to their interconnectedness, and this proportion counterintuitively should be higher in environment where we hypothesize large growth. So the fact that we have large growth doesn't mean that you should have less capital, but rather more capital, because otherwise everybody's going to take even more and more risk, and the system is going to be exposed to high level of systemic risk. And so if you do this, and if you appropriately adapt to the growth and to the connection, then these nodes that have high threshold growth over time, they could act as shock absorbers in the system. Okay, so thank you all, and yeah, so this is for coming on the. This is based on this paper, and it's available online. Okay, so thank you, and I'd be happy to answer if there's any questions.
Let's all thank Andreea.
Wow. Okay. So I see that my cursor has been spared, and I was hoping that you'd have answered all the questions in the chat, but I see there were no questions on the chat. Okay. So,
I have a question, Andreea. Did you also look at kind of how does the structure of the network affect these results, in that suppose instead of looking at like a random configuration model, there was some clustering? Would that exacerbate and make this worse, or is there a way of kind of constructing a network to provide more protection?
So in general, that's what I always say about these random graph approaches, is that, they're very good to point out to qualitative problems that might emerge. But, looking and analyzing given networks that have particular structure and proving, okay, for this network that has this clustering and this particular cluster, we have the same effect. I don't think that this has been done. So it has been done by us, and I don't think there is work on, so not that I know. And especially now with growth. But of course, this is a very interesting direction, because as you can see, what this points out is that this growth is not necessarily is going to lead to surprising effects.
And also, in terms of the the equilibrium behavior, if you were instead to allow agents not only to choose their overall connectivity rate, but also individual, I choose to link to this particular person, would there be a way that the agents would then, in a decentralized way, like try to connect to nodes that are more stable more often. And but I don't know, is that something that could be looked at as well?
So you're asking whether we can look at particular choices, who like might I want to connect to a particular group?
Exactly.
So that would need a slightly modified configuration model, where you'd say, okay, you'd have maybe some two types of links, and then I could choose maybe this type of links to connect to some agents, and this other types of links to connect to some other types of agents. In the basic configuration model, people are just choosing their connectivity, and then who connects to whom comes from a uniform matching. But what you could do, of course, is say you don't want this. You could tweak a little bit this and go away from this uniform matching. Try to put multiple types of links, and then say maybe I have uniform matches among this type, and then try to see what they would do in equilibrium. I think that this is possible, yeah, and then you'd have more insights. But again, what we did was a basic model, and then hopefully there will be more to say about it and more extensions come back.
I guess there are no more questions. We are out of time today, so maybe we'll.
You're always out of time with me, so it's like this is a notorious problem. This is not a new thing. If you go to the SIME conference on financial mathematics, this is notorious there. So yeah, yeah. No surprise there. Okay, thank you all then. Okay,
Thanks,
bye.
Andreea.
Thank you for the invitation.
Bye, everybody.
Right.